All right, a tabletop controls lab by me, Erik Everse.
And me, William Ward.
So the problems we set out to tackle were primarily from a lack of hands-on experience in the classes of EAT 2150 and EAT 4311. These classes, we learned a lot about PID controllers, how they work, the theory behind them, and we used MATLAB to simulate using PID controllers. But what these classes did lack was a hands-on lab to see how they actually work in kind of the real world. So we wanted to enhance the learning through practical application. So this is why we set out to build a lab that we can set on the tabletop, and students can see how PID controllers work and why they might be utilized and how tuning can change the output. We thought this was very important after learning the importance of PID controllers. Through both of our internship experiences and other things that we have seen throughout the university and within the job market, we have seen that PID controllers are a very important thing for us to understand before we go out into the workforce, because PID controllers are found everywhere. That being said, we also believe it could be important for other students to have a very good understanding of PID controllers, and the development of a lab would be beneficial to their education. So the design that we came to was a teeter-totter that will balance a ping pong ball in the middle, utilizing a PID controller. So for the sensor, we have an ultrasonic sensor that will be able to measure the distance to identify where the ping pong ball is. And then this will go to the motor, which will be able to change the level and angle of the teeter-totter to move the ball towards the center. The controller we decided to use for this is MATLAB Simulink and a DAQ board to connect to Simulink.
So some conclusions we came to while we were working on this were that there's a lot of fine tuning that goes into the design of Simulink. So for example, the sensor trying to figure out the distance of the ping pong ball to it so it knows when to tilt up or tilt down. This can be rather tricky because when you change the PID values, it also changes what's considered the middle or where it needs to bounce the ball, not so entirely based on distance at that point. However, when using Simulink, it's a lot easier than I expected. Until about 6 weeks ago, I hadn't really used it, but now I think it's a great tool to use, and I wish I had learned it sooner because it's really straightforward to learn. I think it's my favorite programming language that I've used so far. So some recommendations we have going forward for our final design. We plan on swapping the ball and rail system for a slider, so to speak, where we'll implement two rails on either side and then a flat piece of plastic or other material that will slide along it to measure distance. This way, we don't have the issue of the ball getting knocked off or, not staying within the track. And then also implementing emergency stops so that if the totter tilts too far, it doesn't just keep going and snap. It'll eventually hit a button and, cut power to it. We also plan on using a wooden totter because the 3D print, while it is good in theory, it takes a long time to print, more time than we have. And also using wood is a cheaper option. The other issue we plan on tackling is the linkage that connects to the motor does not quite fit. And we think that using in materials like, metal would be a finer fit and would solve this issue.